In this episode, we begin with a topic that sits quietly underneath a great deal of defensive security work, even though new learners do not always notice it right away. Hashing and file integrity techniques are really about answering a simple but important question. Is this file still the same as it was supposed to be, or has something changed in a way that matters? That question becomes extremely important in cybersecurity because attackers often alter files, replace trusted content, hide malicious code inside legitimate-looking objects, or quietly tamper with system components in ways that are easy to miss unless the organization has a reliable way to detect change. When you understand hashing and integrity at a practical level, you start to see that security is not only about keeping bad things out. It is also about noticing when something inside the environment is no longer what it claims to be, and that ability can make the difference between early detection and a compromise that keeps growing without anyone realizing it. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A useful place to start is with the idea of integrity itself. In cybersecurity, integrity means that information, files, configurations, or system components remain accurate, complete, and unaltered except through authorized and expected changes. In plain language, integrity is about trust and sameness. If a file was approved yesterday, you want confidence that it is still the same approved file today unless a legitimate update occurred. If a security log is meant to preserve evidence, you want assurance that it was not quietly changed after the fact. If an application depends on certain system files, you want to know those files have not been replaced with something malicious or corrupted. For a beginner, integrity is important because many security failures are not only about stolen data. They are also about silent modification. An attacker who changes a startup file, a system library, a configuration, or a business document may create serious damage even if nothing is visibly broken at first, and integrity techniques exist to help reveal those hidden changes. Hashing is one of the most common ways defenders support integrity checking because it gives them a consistent way to represent a file with a compact digital fingerprint. A hash is the output of a mathematical process that takes input data, such as a file, and produces a fixed-length value that changes when the input changes. The exact mathematics can be complex, but the beginner idea is straightforward. If the file changes, even slightly, the hash value should also change in a noticeable way. That makes the hash useful for comparison. You can record the hash of a trusted file at one point in time, then calculate the hash again later and compare the two values. If they match, the file is probably unchanged. If they do not match, something about the file is different. For a new learner, the key point is that a hash is not meant to describe the contents in readable language. It is meant to provide a stable and efficient way to test whether the content appears identical or altered. One of the most important beginner distinctions is the difference between hashing and encryption because people often mix those ideas together at first. Encryption is meant to protect confidentiality by transforming data so authorized parties can later turn it back into readable form. Hashing serves a different purpose. It is primarily about integrity and comparison, not secrecy and recovery. In ordinary use, a hash is treated as one way, which means you use the original data to create the hash, but you do not reverse the hash to reconstruct the original file. That is why a hash can be shared for verification without revealing the contents of the file itself. For a CySA Plus learner, this matters because the same security environment may use both hashing and encryption, but for different reasons. Encryption protects information from being read by the wrong party, while hashing helps detect whether information has changed. Those are related goals inside a larger security strategy, but they are not interchangeable, and confusing them makes it much harder to understand how integrity techniques fit into real defensive practice. Another important concept is that a strong hash reacts very sharply to small changes. If one character changes in a text file, one line is added to a script, or one hidden piece of code is inserted into an executable, the resulting hash should look dramatically different rather than only slightly adjusted. This property is extremely useful because it allows defenders to notice tampering even when the visible file still looks almost the same to a casual user. A malicious program may keep the original name, icon, and apparent purpose of a file while altering its underlying contents enough to change the hash completely. For beginners, this shows why hashing is so practical. Human review is not always reliable for detecting small or hidden modifications, especially across large environments full of thousands of files. Hashing provides a faster and more consistent way to check sameness. It turns the vague question of "does this look different?" into a more precise question of "does the computed fingerprint still match the trusted version we recorded earlier?" Hashing becomes especially valuable when organizations need to establish a baseline of trusted files. A baseline is simply a recorded picture of what should be present and unchanged under normal conditions. The organization might calculate and store hashes for approved operating system files, critical application components, configuration files, or sensitive records at a point when those items are known to be clean and correct. Later, those same files can be checked again to see whether the current state still matches the approved baseline. This helps defenders notice unauthorized change, drift, corruption, or tampering without needing to inspect every file manually each time. For a beginner, this is one of the clearest ways to understand practical file integrity work. The team is not hashing files because it likes mathematical fingerprints for their own sake. It is building a trusted reference, so later comparisons can reveal whether something important in the environment has changed unexpectedly and therefore deserves closer review. A closely related idea is file integrity monitoring, FIM, which refers to the ongoing observation of important files and system objects so that meaningful changes can be detected and reviewed. The value of FIM is that it moves integrity from a one-time check into a continuing security function. Instead of only confirming a file once, the organization monitors whether critical components remain stable over time and whether changes are occurring through approved processes or suspicious ones. This matters because attackers rarely announce when they modify a startup script, replace a legitimate utility, alter a configuration, or tamper with a log file. A good integrity monitoring approach helps surface that activity. For beginners, the most helpful way to think about FIM is as a watchful process that asks whether important files are staying consistent with what the organization expects. If something changes, the next question is not automatically whether that change is malicious. The next question is whether the change was authorized, documented, and consistent with the system's intended use. One of the strongest applications of hashing is in validating known good and known bad files. If the security team knows the hash of an approved system file, it can compare a current copy to that approved fingerprint and determine whether the file appears unchanged. If the team has a hash associated with known malware from previous investigations or intelligence sources, it can search for that same fingerprint across systems to see whether the exact file appears elsewhere in the environment. This is useful because it allows security teams to identify identical content quickly, even when the file name has been changed. For beginners, the key lesson is that file names are easy to manipulate, but content-based comparison is harder to fake. A malicious file can call itself something harmless, but if its underlying content matches a known malicious sample, the hash can expose that match. At the same time, a different hash does not automatically mean a file is safe, because attackers can modify malware to create a new fingerprint while preserving harmful behavior. That leads into one of the limitations beginners need to understand clearly. Hashes are excellent for identifying exact sameness, but they are not magic labels that explain intent by themselves. If a file changes by even a tiny amount, the hash changes too, which means a slightly altered version of malware may no longer match the previous hash even if it is clearly related in purpose. This is why security analysts do not rely on hashing alone when they are trying to understand suspicious content. They use it as one valuable technique alongside static inspection, behavioral analysis, reputation, email context, endpoint evidence, and network observations. Another limitation is that not every changed file is a bad file. Software updates, patches, approved reconfigurations, and normal business edits all change hashes too. For a new learner, this is a very important balance to keep in mind. A changed hash means the file is different, not automatically malicious. Integrity techniques are strongest when they highlight meaningful change, so the analyst can then judge whether that change fits expected operations or suggests compromise. It also helps to distinguish between simple error checking and stronger cryptographic hashing. Many computing environments use checksums or other lightweight methods to detect accidental corruption during storage or transmission. Those techniques can be useful for catching mistakes, but security usually needs something stronger because attackers are not accidental. They are deliberate. A strong cryptographic hash is designed to make it very difficult to find two different inputs that produce the same result in any practical way that defenders would consider acceptable. For beginners, the exact mathematics of collisions do not need to become overwhelming, but the core idea matters. If attackers could easily create malicious content that produced the same hash as a trusted file, integrity checking would lose much of its value. That is why the choice of hashing technique matters. Some older algorithms are no longer trusted for serious security use because weaknesses became better understood over time, and defenders need to use methods that remain strong enough for real-world integrity verification rather than relying on outdated comfort. Hashing is also useful beyond ordinary files because integrity applies to many kinds of digital objects. Configuration files, scripts, logs, database exports, firmware packages, software installers, and sensitive documents can all benefit from integrity checking. A modified configuration may open an unexpected service or weaken an important control. A changed script may create persistence for an attacker. A tampered log may hide traces of compromise. A swapped installer may deliver malware under the appearance of a legitimate update. For a beginner, this broader view matters because file integrity is not limited to classic malware scanning. It is part of how organizations detect silent changes to the digital building blocks they rely on every day. Once you understand that, hashing becomes much more than a feature of file analysis. It becomes a way of asking whether the trusted components of the environment are still trustworthy and whether something beneath the surface has been quietly altered to support misuse, concealment, or future damage. Another important connection is between hashing and incident response. When responders investigate a suspicious system, they often need to determine whether critical files have changed, whether the same suspicious object exists on multiple hosts, and whether evidence collected from one place matches evidence found elsewhere. Hashes help make those comparisons faster and more reliable. If two files on different systems produce the same hash, the team can say they are exact matches at the binary level. If a known clean baseline no longer matches the file on a compromised host, the team has evidence that the host has been altered. For beginners, this shows why integrity techniques matter after an incident begins, not just before. Hashing supports scope determination, evidence comparison, and prioritization. It helps answer practical questions such as, is this suspicious file isolated to one machine or widespread across the environment? And are we dealing with the approved version of this program or a modified one that now behaves differently from what operations expects? Hashing also supports secure software distribution and trust in updates, because organizations need ways to confirm that a file they downloaded or received is the same file the trusted source intended to provide. If an update package, software installer, or document archive is altered during distribution or replaced by something malicious, the hash comparison can reveal that the received copy no longer matches the expected value published by the trusted provider. This kind of verification is not glamorous, but it matters greatly because supply chain risk often depends on attackers inserting themselves into places where users assume trust already exists. For a new learner, the big lesson is that integrity is about more than internal monitoring. It is also about validating the things that come into the environment from outside. A file arriving from a legitimate-looking source may still need integrity verification if the organization wants confidence that the content is authentic and unchanged rather than simply hoping the source and the path remain trustworthy throughout delivery. Several common misconceptions are worth clearing up because they can weaken good security judgment in this area. One misconception is that matching hashes prove a file is safe in every meaningful sense. In reality, they prove sameness, not goodness, and sameness only helps if the reference point was actually trustworthy. Another misconception is that different hashes always mean malicious change, when many routine operations such as updates and edits produce new fingerprints as part of normal business activity. Some learners also assume that hashing can reveal the full content of a file or explain exactly what the file does, which it cannot. A hash is a comparison aid, not a behavioral description. Finally, some people treat integrity checking as a one-time technical task rather than an ongoing security process. For beginners, the healthier mindset is to see hashing as a powerful but limited tool. It is strongest when paired with good baselines, secure storage of trusted values, controlled change management, and human analysis that can separate expected change from suspicious tampering. As you bring all of this together, the lasting takeaway is that hashing and file integrity techniques help defenders answer one of the most important questions in cybersecurity. Has something changed that should not have changed? Hashing provides a compact way to compare digital content, detect alteration, validate trusted baselines, and support investigation when files, configurations, or logs may have been modified. File integrity monitoring extends that idea into an ongoing practice of watching critical components for unauthorized or unexpected change. None of this replaces deeper analysis, because a changed file is not automatically malicious and an unchanged file is only as trustworthy as the baseline behind it. But for someone studying CISA+, the big lesson is clear. Security depends not only on blocking threats at the edge, but also on detecting quiet modification inside the environment. When you understand hashing and integrity techniques, you gain a practical way to notice when trust has been altered, and that ability is often one of the earliest and most valuable signs that something in the environment is no longer what it is supposed to be.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.